Okay, I'll just start. It's my great pleasure to be here today. I'm talking about new research that has me really excited, and it's my honor to be joined by two people I'm honored to call colleagues, Marvin Bolt, the legendary curator of science and technology at the Corning Museum of Glass, now emeritus, and Sandy Chang, a Yale College Associate Dean for Science, a professor of medicine at the Yale Medical School, and also an avid mirror maker who's going to give us the kind of concrete version of what mirror making is actually like, and Giorgio Strano, curator of the historical collections of the Museo Galileo in Florence. And I'm honored to call all of them friends and colleagues. So I'm just going to start, and then each of my co-participants is going to do a little bit of talking, and then the four of us are going to be engaged in a discussion. And the main discussion has to do with this new text that I found, and I'm going to introduce that right now. So first slide. So in pre-modern China, eclipses held prognostic significance. In 1610, a solar eclipse failed to be predicted, and the Ministry of Rites of the Ming Dynasty began seriously considering methods to reform the calendar. By the 1630s, 3 different sets of calculations for predicting solar eclipses were being evaluated. Those predicted by scholars at the Ministry of Rites, by those
camera on finally? Okay.
Hello? Those calculations by Uyghurs using Arabic techniques. And finally, next slide, by the Jesuits, whose main advocate was the Catholic convert and official Xu Guangqi. And here's a picture of a Jesuit and Xu Guangqi together, obviously drawn by an Italian. Eventually, the European calculations were deemed most accurate, but the telescope was vital in evaluating the 3 sets of answers because the timing and magnitude of a solar eclipse cannot be measured with the naked eye without risking blindness. So telescopes were set up to project images of the sun onto a piece of paper or silk, and from that point on, telescopes played an important function at the court. Various court documents mention first next slide, please. Various court documents mention first the telescopes presented by the Jesuits, and then the Ming court's own work to produce more telescopes. But as far as we know, though Marvin's experience may differ, it's a little teaser, none of these telescopes have survived. So in 2017, next slide, please, in the Zhejiang Library, the scholar Gong Yinyan rediscovered an undated manuscript, a copy of Kaichen Jiyao that was attributed to Matteo Ricci and supposedly edited by Xu Guangqi. A few pages of it concerned the making of telescopes. Next slide, please. And the dates, of course, did I say next slide? I'm asking for the next slide, please. The dating of it, of course, makes Ricci's authorship impossible because, of course, Ricci had died in China while Galileo was making his first telescopes. On the basis of echoes between Kaichen Jiyao and established writings of Xu Guangqi, and also the way in which the manuscript was passed down by Xu's descendants, Gong argues that Xu is by far the likeliest author. My guess is that these notes on telescope making date from the very last years of Xu Guangqi's life, around 1630, and are his notes from the state's effort to make telescopes. Next slide, please. So here is Kaichen Jiyao on the process of grinding a lens with mention of all the main components necessary: the mold, the wood holder, the gum to affix glass and wood, the multiple kinds of grit necessary first to grind and then to polish, and of course the water to keep the glass smooth. Grammatically, it translates into straightforward English, but the text makes sense only insofar as the reader already has some basic familiarity with the process. And I'm not going to lie, some parts remain obscure to me. Next slide, please. What does he mean by a kettle pot shape? I'm not sure. Other passages, though they deploy words that are to be found nowhere else in classical Chinese, are quite clear to someone who has some sense of lens fabrication. Here is Xu Guangqi describing gauges. Next slide, please. Again, I'm not sure what he means by stopping only when both curvature gauges match. However, next slide, please. I am certain as to what the author means by 半径尺, which I've translated as a ruler that has the radius marked out, or 曲倍尺, which I have translated as curvature gauge. He means something like the things I saw in the Palazzo Poggi that Campani used to make his own lenses in the middle of the 17th century. The tools on the top are what Xu Guangqi would have called Campani's 曲倍尺, used to gauge curvature, and on the bottom are his 半径尺, pieces of metal that mark the radius length. Xu Guangqi must have learned some of this from a Jesuit, or more than one, with practical lens-making expertise. Next slide, please. One obvious vector for this kind of knowledge would have been Giovanni Paolo Lembo, a Jesuit maker of telescopes, who was known to have taught lens grinding at the Collegio de Santo Antoine in Lisboa, the last stop for many missionaries before traveling to Asia. Next slide, please. Notes taken by a student in his class reveal practical instruction. A graduate of this kind of teaching might easily have had the knowledge that translated into Xu Guangqi's remarks. But a student of Lembo would not have been able to collaborate just with Xu Guangqi. Whether those are words, the technical words that I just explained, were invented by Xu Guangqi or not, they are certainly words that emerged out of conversation with local craftsmen. In other places, too, the text implicates not just the work of craftsmen, but their persons. Next slide, please. Note that a grinder must be sent out, not just that the grinding sand must be acquired. Use the finest polishing sand, which is sold at the jewelry establishments in Suzhou. Nor is it that the polishing sand itself can only be acquired by a grinder. I imagine that this store could only have been known to Xu Guangqi, who never lived in Suzhou, after a craftsman told him about it. So in other words, this text might have been written by one ruling class Chinese man, but it must have been the product of many conversations involving a range of interlocutors. It's easy to imagine this as the unusual case in 17th century China in which an official and an educated man played a relatively marginal role. A student of Lembo's working with the palace and hence the world's most skilled jade craftsman might well have made relatively short work of making a Galilean telescope. But the text emerges out of at least a tripod of contexts. The unnamed Jesuit or multiple Jesuits who had studied with Lembo, palace-affiliated craftsmen who were expert at shaping jade into whatever shape they wanted, and the classically educated Xu Guangqi himself, all of them brought together to complete a complicated and perhaps impossible commission from the Chongzhen Emperor. So the Kaichen Jiyao were not regarded as part of Xu Guangqi's official writings, and according to Gong Yinyan's research, it only survived through a series of unlikely events. Gong Yinyan posits that the text was never edited, never mind published. It was held in the collection of Xu Guangqi's descendant, Xu Chaojun, and these notes were recopied in 1857 by a well-known bibliophile, Han Yingbi. Han Yingbing says, and this is in a little postscript in the manuscript, there are words and phrases that are in error and can't be parsed. It can't be published. I would argue that Han Yingbing simply didn't know what he was reading at all. But at any rate, I'm virtually certain that these notes stayed more or less private, unread by anyone who might use them. My best guess is that any work on telescopes in the palace workshops went on hiatus during the fall of the dynasty in 1644, and after the fall of the dynasty, the craftsmen who had learned from Lembo's students never used their skills again. Xu Guangqi's notes seem not to have been read by anyone for more than a century, and it is striking to me that in these almost 400-year-old notes, we're actually finally in a position to understand them. They record the interactions of a group of people, stone grinders who are jewelry makers, at least one Jesuit, probably more, an official, who brought together disparate skills and knowledge, who came together having grown up learning different things in different languages. And it happens that I have brought together another group of people almost 400 years later with other specialty knowledges to mirror those. Practical knowledge of lens grinding, Sandy, comprehensive knowledge of early telescopes, Marv, knowledge of early modern European lens making, Giorgio, If all texts are messages in bottles flung into the ocean of the future, it feels miraculous that sometimes a group of moderns can sometimes come together and make a landing place for them. Thank you. I think the next person to go should be Marv.
All right, thank you, Tina, for that tour and gracious introduction. My presentation has two components, really. One is strategies for making the lenses, and then the second part is on placing the lenses in the appropriate place. We'll see how far we can get through that in the presentation part, and then also in the Q&A element. So if we can have the second slide, please. All right, thank you. So lenses come in two varieties, really. In the first, on the left side, the function is to gather light and condense it or converge it, and that's called a positive lens because the focal point is on the right side, on the downstream side, if you will. On the other lens, on the right side, the second function of a lens is to diverge light, and it's a negative lens because the focus is on the upstream side. All right, so converging or diverging. And the distance from the lens to that focal point is the crucial detail that we're going to take a look at. So on the next slide, we have a variety of ways in which we can combine positive and negative lenses, but we don't have to worry too much about that here, other than to say that it is possible to combine these in some way. All right, next slide. So magnifiers of some sort have been known since antiquity, and especially in the centuries before the development of spectacles, we have these rock crystals that can be made out of either quartz or beryllium. And then if we click one more, there's an etymological little distinction here, which is, if we can just click that, Scott, that beryllium has lent itself to the Dutch and German word for spectacles, brill. And that's not a coincidence because those early spectacles could either be made out of rock crystal, beryllium, brill, or glass. And it's not always clear which is being used. And this would be a great topic for further research for anyone out there who's interested in this. All right, next, please. So in that next slide, we see that distance from the lens to the focal point plays a crucial role in distinguishing between a magnifier and a spectacle. If we can go to the next slide. This requires us to take a little detour into human vision. So normal vision, visually acute vision, the light coming in from the left side passes through the cornea and the lens and comes to a focus on the back of the eyeball, the retina. Next, please. For those of us who have reached the age of 30 and beyond, we have a little challenge there because the lens and cornea don't quite focus correctly. They're not quite as pliable as they used to be in our youth. And so the focal point happens behind the retina. This can also be if the eyeball is too short. And then finally, a second problem is that the focal point can be, if we can flip the next one, please. The focal point can happen before the retina. Now, why is this of significance? Well, in the next animation, we can see that if we put, the next one, please. Thank you. If we put a converging lens just in front of the eyeball, we can see that it just nudges that focal point to be not behind the retina, but on the retina. And if we show the next concave lens, the diverging lens, if that focal point in the retina is just before the retina, that diverging lens can move it back a little bit beyond. Now, this is just a very, very slight adjustment that we need, all right? Not a huge one. So if we go to the next slide, we have what looks to be a magnifier, at least what we would think of as a magnifier, but notice that this optical device is not on the book itself, but is in front of the eye. It is a vision correction. It is not a magnifier placed next to the object. And if we go to the next slide, we can see another very early illustration, the earliest known illustration of a pair of spectacles found in a scriptorium in Treviso, just north of Venice. And you can get the scale of what these illustrations are like. So now if we go to the next slide, we can see, again, there's two animations here, just a quick double click there, please. We can see that those lenses just make a slight variation as opposed to a magnifier, which has a short focal length and a great variation in the concentration of light. All right, next slide, please. So in the process of grinding, we actually remove a fair amount of glass from the surface so that the shape actually changes. And then in the second and third and subsequent grindings, less and less material gets removed from the glass until in the very final stage, the polishing removes the very small bumps and valleys and smooths them all out. But the grinding stage changes the shape. All right, next slide, please. So there are a couple of variations on how you can actually grind and polish. You can either have the tool, the grinding tool, rotate and the glass be stationary, or you can have the tool be stationary and move the glass. Next slide, please. So the glass would be placed on a little pistol like this and attached to it. And the grinding tool will remove enough glass to change the shape of it. Next slide, please. So the gentle curvature of a spectacle lens is in fact exactly the same curvature as the lens for a telescope objective. It's not that short focal length of a magnifier, but the longer one. For those of you who have eyeglasses and you might have a strength of the glass of 2 diopters, say, that's 100 centimeters divided by 2 or 50 centimeters. That's the focal length of your spectacles, which is exactly the kind of thing you want for a telescope objective. But here's the catch. When you have spectacles, you only have the very central part of the spectacle actually impacting the image that forms on the retina, roughly the same size as your pupil. For a telescope objective, the entire lens produces the image or impacts the image. So any defect that's in the spectacle lens, well, it doesn't have quite the impact that a telescope lens would have. So if you have a small range in your spectacle lens that is of a consistent curvature, you get a good image. But you need that same curvature to be consistent over the entire lens if you want a telescope objective. So if we can go to the next slide, please. Suppose we take a pair of spectacles. This one is from about somewhere in the 15th century. And next, please. We use them to create a telescope. You'll see that it's kind of fuzzy. It's kind of unsharp. It's blurry. But there's a trick to this. And on the next animation, please. What we do is we can test this with a test developed in the 20th century by putting a grid of wires in front of the lens and seeing what that grid of wires looks like. Now, if that lens had a very nice spherical shape, those lines would be straight. And as you can see, those lines here are not very straight at all, resulting in a blurry image. But if we go to the next illustration, please. If in fact we just use the central portion of these lenses and block off the exterior parts, we actually can produce a telescope that enlarges well and enlarges sharply. So next animation. That is to say, if we put a donut or diaphragm over the front of the lens, and then we can do that on the right one too, now we have a telescope. And if we have the last one on this slide, we look at the very oldest telescope that's securely dated, we see that that, in fact, is the strategy. All right, so what's the takeaway from all this? Spectacles appear around 1290s, and within 20 years, they're readily available. In fact, the price of spectacles in 1316 is about 1 day's wage for a common laborer. And if we think of New York State, at least, where the minimum wage is $15 an hour times 820 bucks, that's actually about the price of a pair of glasses, a simple pair of glasses. In fact, for 700 years, the price of glasses has remained roughly the same. So what this means is that you actually have widespread availability of spectacles at a price that's accessible to more people than you might have thought. In fact, we know that thousands of them were made in the 14th, 15th, 16th century. There's a record, in fact, in 1540 of 24,000 spectacles that were shipped from Venice to Constantinople. So these are commonly available devices, but not suitable for telescopes because they couldn't be shaped in a way that makes a telescope possible. So I will do 1 or 2 more slides here, and then we'll get back to telescopes in the Q&A. So if we go to the next slide, please. That's the oldest securely dated telescope in the world. You can see at the left side there how much of the lens is actually blocked. In Tina's text, there is an allusion to that. There's also an allusion to the tubes. And in this case, the tube is made out of cardboard. It's made out of paper. And one of the reasons is that, as you can see here, it's very hard to hold this up for any length of time. And the earliest tubes made out of metal would have been way too heavy to hold for a long period of time. It also consists of multiple tubes that can be drawn in and out. And the last slide we'll take a look at. Next click, please. And the next. And finally, the next. We see that for this, excuse me, for this telescope, the stopping down of that lens matches the stopping down of spectacles made before that time. So we know this is the strategy for making a spectacle into a telescope. And that's all we'll say about the glass, the lenses of telescopes, other than to say these lenses could be made out of either glass or rock crystal, just as the early spectacles could be made out of beryllium or glass. It's not always clear what material is being used for the lenses of these early telescopes. All right, we'll come back to some of these things in the Q&A. Thank you.
Maybe we'll move now to Giorgio.
Hello, can you hear me?
I actually want to show illustrations or photos of a couple of the oldest surviving Chinese telescopes and a couple of observations about that. So could we go to slide 37 in my PowerPoint, please? And while that's coming up, I'll notice in Western traditions, you can have these tubes made of cardboard, wood, metal, gold, silver, even ivory. It indicates a distinction, a division of labor between the glass-making folks and the other kinds of decorative arts that were necessary for putting lenses in the right places, not only for optical reasons, but for aesthetic reasons. Don't know if that's possible to get up that set of slides or not. Oh, great. Thank you. So yeah, there's an ivory one. Next slide would be a gold one that is incredibly heavy, solid gold. And then another one, the next one is silver. we'll go to the next slide, something that has not come up yet, but has been mentioned only in 2 publications that I can find, that when Galileo is actually messing around with a glass composition and complaining that glass gets recycled and therefore it's bad, this is also the time that Antonio Neri is writing The Art of Glassmaking, and Galileo has access to this book, but that connection has not been explored. All right, next slide, which is where I wanted to go. There's a lovely book that's hard to find on the scientific and technical instruments that are in the Palace Museum, the Forbidden City in Beijing. And so the next slide, please. On the right side there, you have probably the 2 earliest telescopes that survived that were made in China. It says it's made out of wood with some lacquer. I've had the chance to look at one of these, but I had about 4 minutes to look at it. I was not allowed to take any photos, and most crucially, I wasn't allowed to take it apart, which is how I really need to look at these to study them. But these are the oldest known ones, and the aesthetic is very interesting. On it, there's a crescent moon with a star shining through the moon, which tells you that the person decorating it isn't really informed about astronomy. And I find that to be really, really interesting. The next slide, please. Here we have on the bottom a telescope that sort of looks European, but is apparently made in the Qing workshop, which has all sorts of interesting things to, it brings up a whole lot of issues that are interesting and merit more discussion. But the one I really want to look at is the top one. So telescopes have to place the lenses at very, very specific locations. And these tubes, when you pull them out, have a little mark on them that tells you how far to pull them apart. That one on the top is traditionally thought of as Japanese. And what's distinct about it is that the tubes aren't cylindrical, but they're conical. That is to say, when they're compacted, the tubes roll and rattle around, but when they're pulled apart, they get tight. It's the only style, or it's the only example of that style. If the label on this is correct, that it's actually made in China, this would be a very, very interesting thing to find out. What it illustrates is that we really have a wide range of expertise that's needed to examine these objects, not just the glass, but the decorative arts aspect, and that there are technology transfers and aesthetic techniques that transfer that really make these topics incredibly interesting and interdisciplinary.
So that first telescope that you showed is labeled early Qing, but there is no way that's a 1650s telescope. That's clearly part of this first push to make telescopes, probably in the 1620s, early 1630s. And it very well is connected to the text that I have been sharing. That seems to me part of that same generation, where there is one record, and I didn't share it in the interest of brevity, of it's clear that they simply had lenses that they brought over from Europe, and they put them into a tube. So, you know, they were talking about making the tube, but not really making the lenses. And then they moved on to trying to make lenses. And it's not actually clear whether they succeeded at any point.
No, that's right. I think that it's a very early one, and we have to get to Beijing. And
I know.
Take me with you, please.
Yeah,
Marvin, I have a question for you. How did they collimate the lenses in an ivory tube telescope?
I wish I knew the answer to that. The ivory telescope that I showed was probably made in Germany, and may have even been made in a royal workshop by royalty, because that was, in fact, a skill that was taught to keep nobility grounded, if you will. So it dates from probably 1650 to 1670, but basic techniques for how you would align these lenses, there is no description anywhere that I've seen. about how to do that. And it's really extraordinary that they were able to do that. That brings up one other topic, and I know we're running out of time. The very first telescope demonstrated in 1608 called for the production of another one that was binocular, because, I mean, let's face it, we have two eyes. We want to see through both of them, and a telescope with only one eye, one optical system, that seemed unthinkable. And apparently Lippershey produced one, but making binoculars is incredibly difficult. There are half a dozen examples that are known from the 17th century, and then it's virtually unknown until the end of the 19th century because it's so difficult. So my answer to that is, how did they do it? Trial and error and luck.
We're still doing it that way.
Well, that's actually the amazing thing, that the kind of, we know Galileo tested hundreds of lenses to find the ones that worked, and that actually now, Sandy, you were describing even, the way that you find out whether the lens curvature is right is you test it. So
Take it out and
I find
test it again.
yeah, I find that really fascinating as well.
It's very tedious. We take it out. Sometimes if you don't have the testing equipment, you could use a star to do it. I actually put the mirror back into a telescope, aim it at a star, and look at the star pattern under very high magnification. I could figure out what's wrong with the mirror. Then we pull it out and grind it polish it some more. So
That's what Galileo did.
Exactly. We're still doing exactly the same thing. Testing equipment just make that not unnecessary. But if you don't have the testing equipment, you still got to do it the old-fashioned.
So we have one more question. I'm trying to find it. Could whoever asked the question just type it in? Because I wonder whether we are actually.
Someone commented about the lens. That's one thing I didn't say is making a mirror is much easier because I only have to make one optical surface. Making a lens, you have to make at least two for the simple lenses. That the telescope that Marvin and Tina, you were showing. But for modern lenses, I have telescopes made out of 3 lenses. That's 6 surfaces you have to polish. Those are the apochromats, and those are the pinnacle of optical telescope making. And that is something that's way beyond the skills of a mere amateur. I mean, I cannot make it's hard. They tell people that if you want to make a lens, a refractor, a lens telescope, go make 2 mirrors first, because the skills you learn from making mirrors will translate very well into making a lens. So I could probably go and make my own first simple lens, but not an apochromat.
So there is a note in Galileo's shopping list that he was looking for pieces of mirror. So if you look for mirrors, you have part of the problem solved in polishing the lens, because one face of the mirror is already grinded and plain. So you only need to grind the second surface to make it convex or concave. So that is a way to simplify the problem.
Mm-hmm. That's right.
And that's mentioned in Tina's text as well. You only want to do one side, probably for that reason. I'll make one last, well, sort of last comment. The spectacles that are in service around the time of the appearance of the telescope, so around 1600, they didn't have to be good, and there wasn't incentive to make them better because your brain can sort of accommodate for imperfections in spectacles. But after the telescope comes, you need better grinding and polishing techniques to have better surfaces. And so the telescope's actually a motivation to improve spectacles as well. And that's, I think, reflected a little bit in that text as well.
Cool. Awesome.
I think